Well, at the risk of using the same phrases that I used this morning, it gives me great pleasure to introduce the next speaker. When we were putting our heads together for this conference, and I think Jeff did a good job this morning telling you about sort of the challenges that we had in putting together this workshop on challenges, and we wanted to have visionaries come and give talks. And so then came across the question, can we get somebody, a visionary on vision? And there were two names that came immediately, and I think they'll attest to this. There was Ulf Grenander and David Mumford. And I thought, well, I'm going to really be ambitious. I met David a long time ago, and I know him, but I thought, I'm going to go to the source, to the man who actually was responsible for David Mumford leaving Harvard after he retired and going to Brown University, and that's Professor Ulf Grenander. You can read a lot of details in the bios. I just want to give you some things that are not on the bios about why I, over the years, have admired this man and his works, because his works have been pioneering. He wrote a book on the role of computers in mathematics, and it's in that series of books on pure and applied mathematics, these famous green books, which you'll find in the library, with books on differential geometry and algebraic topology. And I mean, Professor Grenander is a very outstanding mathematician, and here's a book on computer experiments in math. And you have to put yourself back a number of years ago that computers were looked upon as almost an anathema by pure mathematicians. In fact, David Mumford even was looked upon as doing silly things in his last years at Harvard when he was doing computer experiments. Then there's a series of books called Pattern Theory, which we have learned to love in some of our readings here with my mathematical imaging students. And again, it's pioneering work looking at the structured images, image grammars, and what have you. And then finally, it doesn't end there, because more recently, and I really don't know what Professor Grenander is going to talk about today, but I do hope that he'll mention something about this, is this pioneering work called computational anatomy, where you are trying to model the deformations of people, bodies, okay, in machines, and through continuum mechanics, if you will, or sets of diffeomorphisms, continuum mechanics. And of course, this is very important in the problem of medical image registration. And it started, there's a classic paper by him and Miller that really started a whole new school of thought that's being carried on by other people. Notably, there's a fellow named Christensen in the U.S. So that was the reason why it was pretty unanimous that we really wanted to have Professor Grenander. I thank you very much for your willingness to come and speak to us. So it's a pleasure to you.
Thank you, Ed. As you noticed, Ed mentioned that I am a mathematician. That was intended as a warning. But I'll tell you that I won't do anything very complicated. I only do very simple mathematics, very simple ideas. For a mathematician like me, who has ventured into imaging, and especially medical imaging, it's very sobering occasionally to hear people talk about it, people who actually do it. And today's first speaker, Dr. Babin, told me lots of things that I didn't know, and I really needed that, I think. Now, the topic of this conference is grand mathematical challenges in medical imaging, and you can ask, are there any? Or you could make, as we do in mathematics, we have this problem, we can't solve it, we make it more general, and it's easier sometimes. Well, here, let's make the question into, are there any mathematical challenges in biology in general, or biology and medicine? Now, if you had asked that about physics, there wouldn't be any doubt. I mean, it would be, the answer would be a resounding yes. Well, It was not always like that. If you go back to the late 19th century, actually I wasn't born then, as you might think, but I wasn't, nor did I take part in the Civil War, as my granddaughter asked me the other day. But at the end of the 19th century, then... oh, yeah. What do I do? Just hit a key? Oh, no.
We've got the clip for this now, so I'll just put this on here. Here we go.
I wonder if the power is on.
Yeah, it's okay. It's
Is the power on?
you got lonely. Oh, okay, the battery's
No, I think it's the power. Is the light on my?
yeah? Oh, okay. Sorry about that.
Well, perhaps it's coming back. When my graduate students started to give talks, I told them the first time they give a talk, never rely on mechanical devices, because it doesn't work. Have a backup. I actually have a backup. I have a CD, so I could run on another laptop if needed. Well, anyway, I was going to say that around 1900, or a little earlier, perhaps 1880, it wasn't obvious that mathematics would play an important role in physics. There was some German professor whose name I can't remember, who pointed out that mathematics it's okay in mechanics, where you can use Newton's calculus. But in other fields, more complicated phenomena, for example, in magnetism or in theory of heat, we can't expect mathematics to help. It's too crude an instrument. We need something else. We need more of our physical intuition than any differential equations or whatever. Well, you know what happened. Around the time of the birth of quantum mechanics, then things really changed in physics. There was a period where the Nobel Prize in physics was given only to experimentalists. That's experiments. That's what physicist gentlemen do. The other people have some peculiar things going on with mathematical abstractions. And you can see it. Now you can actually read the Nobel Committee and their discussion of the various experimentalists, good people, versus the theorists, little more suspicious characters. But of course today it's completely different. Now, is the same thing going to happen in biology and medicine? Perhaps I'm preaching to the converted. I don't know. I don't know if you are converted to mathematics. But I think it must be admitted that in spite of the fact that mathematics has been applied to biology for many, many years, it hasn't been quite accepted in the same way as the quantum mechanics people have accepted the Hilbert space theory and so on as a natural tool. I remember I actually met him, one of the pioneers in mathematical biology. His name was Nicholas Rashevsky. He was a very interesting man with an extremely ambitious program. He wanted to make biology into a mathematical science. And he wrote a book called Mathematical Biophysics. It was a wonderful idea. I was really impressed. But the real biologists, the wet biologists, seem to be less impressed. And the book, I don't know if anyone reads that book any longer. I'm sure that working biologists don't seem it. They probably aren't particularly interested in the things that happened in that book. Personally, I used to work with some very good medical people in Stockholm when I was young. In particular, there was a neurophysiologist von Euler who got the Nobel Prize in Medicine later on. He discovered the first signal substance in the brain. And I helped them with very pedestrian things, doing statistical analysis of experimental data. You know, t-tests, analysis of variance, actually very boring things, but useful but boring. And I asked von Euler, couldn't you think of something more challenging, something where we could actually contribute mathematics to biology? And he was quite clear, no, it's too early, it's much too early, but come back in 50 years, and that's exactly what I have done. I've also noticed a sea change in the attitude of medical people that I meet. I meet lots of medical people, both in my friends and colleagues and so on, and they have a different attitude nowadays to mathematics, especially the younger ones. They're not afraid. They're not afraid in the same way they used to be. And it must have something to do with computers. I mean, computers, that's not the same thing as mathematics, but it's a similar activity. And they certainly use computers all the time and other types of electronic machinery. So it's much easier nowadays to communicate. And I've had some very interesting collaborations with not just radiologists, which is rather obvious because of the medical imaging, but also other people, psychiatrists and people like that. Now, I want to be more concrete now. This is general, vague philosophy. I want to be more concrete. I would like to give you an example of a subfield, a subfield of medical imaging, where mathematics may play a role. I warn you that this is a work in progress. It's not at all complete. Perhaps it won't work. As a matter of fact, we've had some difficulty in getting data, which may surprise you, since there are millions of MRIs out there, and some of them are available. But it's not so easy to get good images taken under controlled conditions. After all, these patients are people. You can't do experiment. You can't control all the external variables, and well, there's nothing you can do about that, except that more recently we have been working with mice. That's easier. You can do whatever you want. The poor mouse. Now let's say that we observe. We have some sort of camera. Doesn't matter. Some sort of camera, and we take a picture of the mouse brain or some other organ. And we want to let's talk about 2 dimensions. I mean, the real thing is 3, or perhaps 4 if you have time. But let's talk about 2. That's hard enough. So we have a picture. We have a picture. Let's call it I. And we observe it, and we have in some region of the plane, or of course it should be 3 space, but let's say the plane, we have got that picture using some camera. Perhaps it's scalar valued, could be vector valued. Who knows? It could have other types of values too. It can be quite complicated depending upon whether it's just anatomical or it's more physiology or function, or who knows. Now, obviously what we want to do is we want to make inferences from the observation that we have. And I should add, of course I realize that our observation does not consist of a picture only. We know the patient is 56-year-old male and had cancer of the lung or something. We know other things, but this is, since, as I said, I am a mathematician, so I'm allowed to abstract from everything. Now, the way I would like to think of the genesis of our observation is as a transformation of some ideal image using various transformations. And they could be many. And very often we can organize them mathematically into groups of transformations. I'm not saying that we always can do that, but in some cases we can. For example, we can have the special Euclidean group. That means translations and rotations, nothing else. We can have that working on the original image. So that's a matter that's taking care of registration. Or we can have the multiplicative group just multiplying the values, or perhaps the logarithms of the values by a positive constant. This would take care of some of the photometric variation. Of course, in real images, it's much more complicated than that, especially in the case I'm interested in, and that is in growth. I'm interested in a situation where we have an animal, we have observed it at two different times. So something has happened in between, and we want to characterize that growth. First of all, we want to find that transformation, and second, we want to find deviations from, so to speak, normal transformations. We want to see whether pathologies have occurred or something. So this should, of course, be something much more complicated. Then we have the growth itself. And that I'm thinking of as diffeomorphic mappings. So that means mappings that are continuous and differentiable in both directions. I think that's a good condition. Then we may have semigroups. These are not groups, but semigroups that create new material. A tumor, or something is dying, and so on. And there could be other effects like that. And finally, we have the camera noise, which is probably the easiest one, because those people who are building these machines, they seem to know, at least they claim that they know what the noise properties are, and I believe them so far. Okay, so now we proceed by putting probability measures on these groups, and perhaps on other origins of variability that we happen to have. I don't want to be too concrete here. I don't want to be too detailed, because, as I said, this is work in progress. I'm not claiming that this is what's going to happen. That this is going to be used. I'm not claiming that. My purpose is another, and I'm coming back to that. So now, if we had a probability measure like that, we have then we can say we have an anatomical textbook in digital form, and of course that has to be stratified over a patient population, age and gender and lots and early medical history and so on. So it's a very big stratification. But if we had that, let's be optimistic. Let's say we had that, then in principle we would do statistical inference in the sense of going from the image, compute the posterior probability of the original unknown ideal image, and do something about that. Perhaps just print it. Perhaps print the most likely. That's called a map, M-A-P, most likely posterior probability. or it can be you can do other things. But how do we get there? It's a long story in between. Talking about these groups and their probabilistic properties on the one hand, and the calculations of posterior probabilities on the other hand. I don't know if anyone here is interested in the controversy that has surrounded Bayesian methods, but there has been a lot of controversy, and I think one reason why people didn't use it was just it's so difficult to compute. Well, it shouldn't be so difficult to compute now. It's not easy, I'm not saying that, but it's doable. One way of doing it was the following. Let's talk not of probabilities, but of energy. So that's just minus log. We borrow ideas from statistical mechanics. And then we assume that the energies, that is expressing the prior probabilities, that they are governed by criteria like this. Phi is the mapping. Phi is the mapping from the ideal to the observed image. So the gradient expresses the smoothness. And now we take the norm squared and integrate over the whole picture, and we get a measure of smoothness. We want to make that small, perhaps. That's not so obvious, but I think what I'm talking about so far is about 10 or 12 years ago, and then at that time we thought that was obviously the thing to do. Christiansen, who was a graduate student of Michael Miller. He wrote a wonderful thesis about how to do this. And then we have the deformation. Here's the observed image. This is the mapped image, the ideally mapped image. That means composition, function composition. By the way, that's something that's going to come back here several times. Function composition, not multiplication of functions, but composition, which is more complicated, unfortunately. Yeah. And then we minimize, for example, the sum of those energies, or perhaps there are other energies involved. We minimize that using some algorithm, which I'm not going to discuss. It's not so easy, but it has been done, and it can be computed in 3D, in 4D. So that's okay. But this is not quite the sort of thing that. I loved this a dozen years ago. I thought it was great. No, it was not so bad. But where's the biology? Mathematics is fine, especially for us who are paid for doing it. But where's the biology? And also, if you carry out this program, as has been done, then you will see, unfortunately, that sometimes these mappings are not bijective. That is, they overlap. This image is overlapped into another sometimes. And that happens now and then. That's obviously meaningless, and we have to do something else. And then the next step, which is advocated by the imaging group at Johns Hopkins, is to do the following. Instead of just having one mapping, we think of a flow, so that the image that we had originally, the ideal one, is flowing continuously into the other one. Then you won't get overlap. That's typical of flows. On the other hand, now we have one more variable. We have the time variable. It's not real biological time, it's a sort of algorithmic time indicating how the flow occurs. And then the energies look a little different. Like this, and there will be a relation. The velocity field here gives rise to the deformation in time. So we think of this continuous flow, not breaking up the image. So now we should minimize sum of integrals subject to a partial differential equation. This is called large deformations, because the previous approach was valid for small deformations, but this one is valid for large deformations. So if we had growth over a long time interval, then we would expect a large deformation, and something like this would be needed. Well, this is certainly more satisfactory than the method I just mentioned. But even here, it's difficult to see any biological justification for it. So back to the old drawing board. Let's think of what's going on in the rats, in the mouse brain, or some other cellular assembly. Well, cells can split, they can divide, they can change their shape, but not that much, I suppose. They can move, and they can die. So there are certain elementary operations that we expect to take place on the cellular level. I'm not saying that this model, I haven't presented it yet, but when we get to it, I'm not saying that this model should go down to the cellular level. Perhaps that would be too ambitious. Perhaps one should wait another 50 years for that. But we can think about it. And then suppose we have these elementary transformations like mitosis and other things. Call them something. Call the transformation phi with some superscript here. Don't read that. Then we will have one such transformation composed with another one and another one and so on, and we have a whole family of compositions of transformations. Okay. But one other thing, I think in order to make this feasible, and this is a very ambitious project which has only begun, we need better coordinate systems. Of course, we have ordinary Cartesian coordinate systems, and we have even methods for placing the coordinate system in the brain, the telluric system and other systems. So there are ways of doing that. But again, I don't quite see the biology in them. I would like to have a coordinate system that moves, that changes as the organism grows. And it should, so we start with something, here's an embryo or something, and we start with a coordinate system that is well adapted to the anatomy. And then some growth occurs. We don't know exactly what happens, but it's certainly of that type. But of course that doesn't say very much, because I haven't said what they really are. So combine them together, we should get a growth model, and the coordinate system is going to develop. I'm going to call that type of coordinate system Darcian. And that's in memory of the great pioneer in the study of shape, Darcy Thompson, the Englishman who wrote his book On Growth and Form. Perhaps it was in 1918 or something like that, so it's a long time ago. He has wonderful pictures, and those pictures will be seen as very reminiscent of the pictures that we produce now. You will see some of them here. Of course, he didn't have the mathematics. He didn't have that, but he had a wonderful insight into what was going on. So Darcian coordinates. Now, to make this understandable, I would like to have examples, a few examples. I have 15 minutes, do I?
25 after, yeah.
Mm-hmm, yeah. So let's take a look at some pictures here. Let's say we start with something completely abstract. I mean, this is not my approximation of an elephant. It's not. It's not an approximation of anything, but it's a good thing to start with. This is an ordinary coordinate system. We have two coordinates. We have radial coordinates in that direction, and we have angular coordinates along here. And we can think of this as a slice. We think of this as a slice. And here's another one. This is actually taken from a mouse brain slice, taking just the boundary of it here, the boundary, and then computing a Darcian coordinate system which is going to look like this. You see the idea. You probably don't see how it's done, but you can see what we want to have. The model, we call it GRID, growth of random iterated diffeomorphisms, is, and I've said this before once, we start with some very elementary operations. X is vector valued perhaps in a Cartesian coordinate system. Xi here is a Darcian coordinate. So these are different things. The organism, this is really a relativity assumption. The organism doesn't know absolute space. It doesn't operate in X, it operates in Xi, because that's where the biology is. The biology is sitting there in the X's as the DNA is distributed and as genes are turned off and on. And as the system changes, then the Darcian coordinate system changes along with it, as you will see in a moment. And here's a special case. It's okay. It says that we make the elementary transformation as for example, not just a cell. I'm probably thinking of cell aggregates. So we are on a slightly higher level now. Perhaps it grows like that, or perhaps it changes shape like that. We have some assumption here, and we build it into something more general. You don't have to read those formulas, and you certainly don't have to read this. But for those of you who are mathematically minded, what we are doing here is something slightly interesting. We take all these elementary transformations that have biological relevance, then we compose them together in all possible ways. That's called the algebraic closure. And then we take limits of them. That's called the topological closure. So what we do is we get a transformation space here. That's algebraic closure and topological closure. We get an interesting mathematical object, and this is the basis for what follows. Now we put probability measures on these things. So an elementary transformation starts with a seed, and then it's growing or perhaps decreasing, who knows, around that seed. But we distribute those seeds according to a Poisson process with an intensity that describes the genetic setup. Well, that's a tall order to do that. I don't know if that's ever possible. However, we can go backwards. We can try to estimate those Poisson intensities from data, see what we get. Okay, so now we have a model of growth. Now this model is actually completely specified. I haven't given you all the details, but it is completely specified, and that means that it can be rejected. I mean, a theory has to be, must be possible to reject the theory, otherwise also use scientific theory. It can't be rejected. And perhaps it will be. We don't know yet. Here's a growth process. Do you see the little stars there? Those are the seeds. And he has this is a growth process here, and this is something the opposite. Let's do it again if I can. Can I do it again?
You know the location of those seeds in time?
No. Yeah. And you see how the Darcian coordinate system follows along, carrying the genetic information out from its original position. So the laws here are expressed not in absolute Cartesian coordinates, but as these curvilinear coordinates. Yes?
So you know the locations of these seeds.
I'll come up so I can hear what you say.
You know the locations of these seeds in time, which means that you know that this point is the same as the point in the next image. These are the same points.
Well, in the Darcian coordinate system, that statement is true. So that, for example, if you follow in the mouse brain, you follow the hippocampus. The hippocampus is going to be expressed by three. Well, that's in three space, so three coordinates. But it's the same idea as here. Three coordinates, and the hippocampus at the beginning is given as some subset of that three-dimensional space. But that subset remains the same during growth. The Cartesian coordinates, of course, will not remain the same, but the Darcian, they will remain the same. And I think this is going to help. Now let's take I don't know if I should talk about this, but as a mathematician, there's certain questions, certain problems I can't avoid. I have to do them when I see them. It's like Pavlov's dog. I salivate when I see certain mathematical problems. And for example, here in an organism, in a biological organism, you obviously will have lots of cells or cell assemblies, and you will have lots of transformations. So it's a large number. Well, in probability theory, we deal with that sort of thing. We have the law of large numbers, which I've alluded to here somewhere. Law of large numbers. And if we did the mathematics, and I should tell you that the way I've done the mathematics would not be acceptable in a PhD thesis. It's so sloppy, but I think it leads to this differential equation, which is going to play an important role, and I call that equation the thermodynamic limit. It's as in statistical mechanics, you have lots of molecules vibrating and moving around, and if the number is big, it's so big, then it depends like a deterministic system. That's thermodynamic limit. Okay, I don't know if I should mention that. Here's the same figure that you've already seen, and now with certain assumptions about the seed distribution and the genetic setup and so on, we can run the growth. I'll get something like that for a short time interval. Or this one. Yeah. Here's a slice of the forearm, and to introduce a Darcian coordinate system there, think of it like this. I have these two bones here, radius and the ulna, and then I have a layer here, so that there are several regions here. 1, 2, 3, 4 different regions. So the Darcian coordinate system is going to be more complicated, of course, and this is the way it's going to look. This is not a very good picture because I couldn't, I didn't have time to do a better one. But you see that here we have actually a coordinate system with 3 singular points. We have a point inside here and a point inside here, but we also have a point here which to some geometers is known as a saddle point. And I think this is, to me, this sounds like the right way of introducing coordinates in anatomies, but perhaps I'm wrong. Okay, so now I'm almost finished. First of all, what we want to do is to get a better feeling for the mathematical structure of that grid space that I mentioned before. We don't know much about it. We know certain things. We can characterize some of those transformations belonging to the grid space. For example, in the simplest case, they are all irrotational. Things like that. We want to prove probabilistic or statistical limit theorems. I've already mentioned one, namely the law of large numbers, but we would also like to prove something that would correspond to the central limit theorem in probability theory, namely that deals with sums or sums of random quantities. Well, here we don't have sums, we have compositions. It's really interesting. It's a different world, and I think again I have a proof that probably shouldn't be published because it's so sketchy, but it seems to indicate that the Jacobian is going to be asymptotically log normal distributed. Things like that. And this number 3, of course, is important because that's when we have data, and as I said before, our data, I guess they are okay, but they are not perfect. If data are available, then we should be able to build algorithms for detecting pathologies. I mean, just detecting, that is, making the radiologist aware of there's a certain point there, a certain area where he should look carefully. So Dr. Babin will be happy to hear that we are not trying to eliminate the radiologists. On the contrary, we are giving them a new tool. Perhaps it's a useless tool. That remains to be seen. And then, of course, to write code. We are writing lots and lots of code. Nowadays, I don't teach. I don't have graduate students. I have to write all the code myself. But that's okay. Now, here's the challenge, and this is the end of my talk. What I suggest that we should do is we should build image processing techniques on biologically relevant models. Perhaps it's a growth as here, or perhaps it's static. Who knows? But something that's closer to the biology than the methods that Michael Miller and I advanced 12 years ago. And then, of course, we should be more careful about the computing. These three-dimensional or four-dimensional problems require a lot of computing. When we started, we used parallel computers. Actually, we had our students build them from scratch, very cheap and very good. These were not advanced parallel machines like the that what's called the thinking machine. Was it called that thinking machine at MIT? Yeah. Our computers had fixed configuration, so that you had one computer sitting here and could communicate with 8 neighbors, nothing else. So that means, but they were easy to program. You wrote Fortran, sort of parallel Fortran, and it was very easy. But of course, that should be done, in a better way, and we haven't even started that yet. So this is, as I said, work in progress. I think it's promising, but we don't know where we will be 50 years from now. Thank you.